Oh, thanks, Clay. Okay, right, today we're actually going to be talking about pumps. So we're going to be talking about what the heck goes on when we're actually trying to figure out which pump we're going to buy. Now, we'll just do a couple of introductions first. And Stu, I'm sorry I didn't have your slide. So what I'm going to do, Stu, I was going to ask you to introduce yourself without any background information.
Good morning, everybody. Thanks for joining us here. My name is Stu Watson. I also work for John M. Campbell Petroskills, and I've been working with them since about 2009. My background is mechanical engineering from Australia. Started working with Shell Australia, and then ended up leaving and moving to the US in around 2000. Various gas processing projects from operations to actual greenfield construction and design work. My involvement here on these webinars is to try and help in the background with some of the technical questions. So if you've got questions, please push them into the Q&A, and I will be trying to keep up with them all in there. Sometimes we get more questions than we can keep up with. Anyway, looking forward to this one, Ron. Thanks so much.
All right, thanks, Stu. A little bit about my background. I'm the head of facilities training for John M. Campbell Petroskills, and I've been around for quite a while. I actually started my working life in 1970. That seems a lifetime ago. I started off with Shell in Shell tankers. So I've played around with pumps in the early days as a user, and most of my work in the early days was troubleshooting pumps. So what we're going to do is we're going to bring in some of the design issues and also some of the troubleshooting issues. We'll bring them together. After I left Shell tankers, I went to still with Shell in PDO in Oman. I ended up being head of technical services. And when I left then, I started my own engineering consultancy until I was picked up by John M. Campbell's in 2011. And actually, at one time, Stu was my boss. It's funny how things go, but that's okay. So I've been doing training for quite a long time. I'm a mechanical engineer. And what I'm going to try and do is try and bring some of my experience to play here, and hopefully it's going to be useful to you. Right, the objectives of this session. What are we trying to do? Right, I think we've all been there at one stage when either we have selected a pump that didn't do the job quite properly, or we're calling the project engineer some really bad names because the pump he selected or she selected didn't work either. So what we're going to do is we're going to go through the process of selecting a pump based on hydraulics. I'm not looking at materials. I'm not looking at intrinsic safety. I'm not looking at any of those things, just the hydraulics. So we're going to develop a system curve, and we're going to use that to help us choose the right pump. That's also going to have some other implications, and we're going to talk about the implications if we choose the wrong pump, that we might get problems with cavitation, you might get problems with seal failures, and we'll see why that happens. And at the end of it, what we want is a pump that's going to be correct, it's going to be applicable, it's going to be useful for all of those operating conditions. So that's our objectives. So let's start. Let's start simply, just a quick reminder, what is a pump curve? Because remember, we're going to develop a system curve. And a system curve depends on your particular system. The pump vendor cannot tell you what your system curve is. You have to do this, but the pump curve, the vendor will tell you. Ideally, if you've got a centrifugal pump, then the centrifugal pump has an ideal performance curve, which is a flat line. But because of friction losses, shock losses, and so on, you're not going to get a flat line. You're going to get something like this. It's going to depend on specific speed and all sorts of other things. You can change that pump curve by changing the speed or changing the impeller diameter. So this is important to know. And when we're looking at the pump curve, we've got a curve with a vertical axis, which is head. You could use pressure, but we tend to use head. The bottom axis is volumetric flow rate. So now we can say if we change the flow rate, we can change the total head that the pump develops. That's going to be useful, and that's going to be something we're going to look at. But if you look at the shape of that curve, keep that in mind, and then look over to the right. And what we see there is a positive displacement pump. Now, I don't care if it's a recip or a rotary, it's a positive displacement pump. And look at the shape of the pump curve now. The ideal pump curve is a vertical line, because a positive displacement pump will always give you the same volume flow rate. Now, of course, because of leakage and slippage, you won't quite get that. And so what you find is the pump curve angles slightly over towards the left. You can change the pump curve by changing the speed. But your options there, well, it's pretty well limited. So what we've got is a centrifugal pump curve or a positive displacement pump curve. I'm going to concentrate mainly on the centrifugal pumps. And I want to explore first of all, what's this thing about head? Because a lot of people get confused about the difference between head and pressure. Okay, head. When we say head, what we're talking about is energy. And if we look at these units, in fact, if my little marker is still working, if I've got head there, in SI units, we use meters. Where that comes from, really I should be using kilonewton meters there, but we could use kilogram meters. Kilogram meters of energy that we put into the liquid for every kilogram of mass of that liquid. So what we do is we cancel out the kilograms and we end up with meters. If we're using FPS, do the same thing, but it's foot-pounds or pound-feet per pound of liquid, and what we end up with is feet. So what you could do is you could think of this term head as being the amount of energy that we're putting into the liquid. But there's an easier way. If we think of a tank that's full of liquid, and I've got a tank here, and I've got a level on here of about 10 meters, about 30 feet. It's fresh water. It's got a specific gravity of 1. Right at the bottom of that tank, I can figure out what the pressure is going to be. And because I've selected 9.81 meters and the specific gravity is 1, I know that that is going to be around about atmospheric. So we're going to get a bunch of pressure. In fact, I should actually do my calcs again on that one, but you're going to get 1 atmosphere approximately at the bottom of that tank. The other thing I want to remind you of is total dynamic head. That is the head on the discharge minus the head on the suction. So that total dynamic head is a measure of the total amount of energy that we're going to put into the liquid. Okay, let's get moving. Right. So, pressure head relationship. Let's say we've got 2 pumps here. And these 2 pumps are both running at the same speed. I've got pump A and I've got pump B. They're both running at the same speed, but they're identical pumps. But one of them is pumping fresh water, and the other one is pumping an oil with a specific gravity of 0.8. What we'll find is that the pressure that the pump has on the discharge, assuming everything else is identical, the pressure on the pump with the high SG, 345 kPa, with a lower SG, 276 kPa. Now remember, we're putting the same amount of specific energy in. That's kilojoules per kilogram or meters or feet, whatever you want to call it. But what we've got is for the same head, the pressure depends on the specific gravity. Now I've got a question for you guys. Which pump is moving the most flow? And just to make this easier, I'm going to ask you guys to select either the tick or the cross. Now you notice at the bottom of your participant list, if you've got one there, do you guys have access to this? I'm not actually sure if you do, but if you can, just press the tick if you think pump A is moving the most flow. Press the cross if you think pump B is moving the most flow. Okay, at the moment I've got a lot of crosses. A lot of people think pump B is moving the most flow. Do you have any ticks at all? I've got a couple of ticks. And I've got a couple of question marks. I'm sorry, guys, but you're all wrong. Because they're pumping exactly the same amount of flow. Remember what we said? It's the amount of head that is the amount of energy. And if we look at the pump curve, we've got head against flow. By doing that, what we've done is we've said for that amount of head, or in this case it's 35 meters or 115.5 feet, that will give us this much flow. So it's going to be the same. And that's quite important. Right, let's go down and just change the scenario a little bit. What we now have are two pumps delivering the same pressure but different heads. Interesting now. Now, my question now is a little bit different. Which pump's using the most power? Tick for pump A, cross for pump B. And I'm not going to make you go through all this again. Because it's the same. The flows are going to be different. But if you look at this formula here, power is flow in gallons per minute multiplied by the differential pressure. And then we got some unit conversions under there. Don't forget the pump efficiency. So power that the pump needs to move this liquid is flow times differential pressure. A couple of interesting things there. Okay, so what we've been looking at now is these issues with pump curves. We've talked about head, we've talked about pressure. There's a reason why I'm doing this, why I'm going on and banging on so much about this thing called head. Why on earth do we get these pump curves from the vendors in head instead of pressure? Well, if let's say we did, let's say that we got pump curve in terms of pressure against flow rate. Well, if that's the case, we've got a bit of an issue here. Because if we have different specific gravities, so say, for example, you're pumping crude oil, and the crude oil specific gravity changes a little bit from day to day. It'll change as the reservoir changes. If you're hooking in different wells, the SG is going to change. If you're working in a refinery and you find that one day you're pumping propane, the next day you're pumping butane, you need different pump curves. But if you present this in terms of head instead of pressure, you have one pump curve. Now, isn't that nicer? That's a lot sweeter. So what you're going to do, and the reason for going through all this, is that I am going to develop a system curve. And by developing the system curve, I've got to figure out what are the best units to do this in. We're going to use head. Okay. So we got a fairly basic system. We're going to go from a storage tank through a pump, and we're going to pump up to another tank. It's going to be a pressurized vessel. And the first thing we've got to think about is what information do I need to be able to help me select this pump? The first thing we do is we say, well, this is a system. I've got my system, I split it into two halves. I could put a line in the middle, and I could look at the suction side, and I could look at the discharge side. Because remember, the total dynamic head is the head on the discharge minus the head on the suction. If I know the total amount of energy, I need then to figure out the total amount of power that will help me. Okay, so what do I need? Well, I need to know how much energy do I have to put in, and I want that in terms of head. So let's think of old Bernoulli. Remember Bernoulli when you went to college? Well, here he is again. Okay, what we've got is just a little bit about the nomenclature we're using here. P for pressure, Z or Z, depending which part of the world you're on, for elevation. So what we've got is our normal liquid level in the suction tank. That's giving me the elevation head. I've got the pressure inside this tank. On the discharge side, I've got some friction losses here. On the suction side, I've got some friction losses there. As we go further down the discharge side, I need to know what the pressure is in that vessel, and I also need to know how high is this liquid going to be pumped. Because if I've got that liquid level here, and I've got to pump up to that level, I've got to put enough energy into my liquid to get it to reach that high altitude. The difference in pressure from the suction to the discharge, again, I have to add enough energy in there just so I can get that liquid into the vessel with that high pressure. And then we've got our friction losses. As soon as the pump starts to operate and liquid starts to flow through that system, then we are going to get some losses. And again, I've got to add energy into the liquid to overcome those losses. So we said the total dynamic head is the head on the discharge minus the head on the suction. And the suction head is elevation plus the pressure. There's something we haven't really mentioned, which is velocity head. I add all those three together, and then I subtract the friction losses. What this is telling me is how much energy does my liquid have right here at the suction to the pump. On the discharge side, I've got exactly the same elevation, pressure, velocity head, and friction. But now notice I'm adding the friction losses. I'm not subtracting, as we did over here. Because I've done that, that's because we're measuring the amount of energy that the pump has to put into the liquid at the discharge. And because we're at the start of the pipe here, we have to overcome those friction losses, so they're all additive. Now, if we've got that, we've got a lot of information. But don't forget all the other stuff. Have you got a suction strainer there? You're going to lose energy as the liquid goes through the suction strainer. You're going to get a pressure drop. You've got a flow meter there, an orifice plate. You're going to have more friction losses and so on. Even exit losses going into this vessel at the end. And you also notice what we've done here with the suction and discharge velocity heads. I've ignored them. And the reason is the velocity energy going into the suction is going to be virtually the same as the velocity energy coming out the discharge. So the difference between them is going to be virtually the same. You might have one pipe size difference, which means that the velocity on the discharge will be a little bit higher, but it's not a lot. And if you think about the calculation for velocity head, so velocity head is V squared over 2G. Let's say you've got a velocity of, let's say, I don't know, 3 meters per second. That's pretty quick. So that'll be 3 squared over 2 times 9.81. That's going to be approximately equal to half a meter. And that's at the suction or at the discharge. The difference between them is negligible, and that's why we ignore them. Excuse me, guys, I've got a bit of a cough. So let's do an example. All right, this example, we've got a suction tank, 50 psi, 345 kPa. We've got 3 meters of head from the liquid level to the pump suction, and I've got friction losses of 0.6 meters. Now that's our formula that we're going to work with. We've got all the information here that we need. We're also being given the specific gravity is 0.7. I need that because some of these things are in pressure, some of them are in head, and I want everything to be in terms of head. So if we just concentrate with the SI units, the suction pressure, 345 kPa, I'm going to convert this to absolute. So I'm going to add the pressure of atmospheric, 101.3 kPa. Anyway, that comes out at 65 meters. If we then add all this together, I've got my elevation head, which is 3 meters. I've got my suction pressure head, which is 65 meters. My velocity head I'm ignoring. The friction losses we said were 0.6. It gives us a suction head of 67.4 meters. Now, for those of you guys who like to work in feet, the same numbers are here on the right side. Sorry, excuse me, guys. Sorry, it's not COVID. I've not been anywhere near President Trump. I just had a little bit of a nose cold last week. Anyway, and you can't catch it through the electronic lines anyway, so don't worry. On the discharge, we got the same sort of thing, but what we've got here is friction losses, we've got line losses, we've got exit losses, the elevation 22.9 meters, and we got almost 7,000 kPa in the vessel. Do exactly the same thing. It's the same formula, except now we have a positive there. If I take my 6895, which is the pressure in the vessel, make it atmospheric, 35 kPa for the exit losses into the vessel, 41.5, which are my line losses, and 103 because this is what's going through the control valve. Divide by 9.81 by 0.7 because all this is, guys, is pressure equals rho G H. Simple. I'm going to have to move my clock now, aren't I? I knew that was a bad idea. Okay. So what we've got now is we've got the elevation, 22.9. We've got the total pressures, which are converted into head. And now we get 1,066.9, which comes out at 7,225 kPa G, if you want to go that way. But it's 1,066.9. Now remember, we had 67.4 on the suction, 1,066 on the discharge, which gives us a total dynamic head of 999.5 meters. Fantastic. This has given me an operating point. So for that particular flow, I've got that particular amount of friction loss. The pressure head and the elevation heads do not change with flow. So they don't worry. It's only the friction head that changes. And in fact, when we look at this is quite easy, isn't it? Because the height or the elevation of the liquid levels, I can measure. I've got liquid level gauges. The amount of pressure in the vessel, I can figure that out. I've got pressure gauges. It's the friction that's the problem. That does become problematic. Right, so what we're going to do is we're going to do some calculations and we're going to figure out the friction head losses here, guys. Now, remember back to your days at school. Your chemical engineers and your mechanical engineers are all familiar with this. And remember the story of Monsieur Darcy in France a few hundred years ago. He figured out a way of piping fresh water to his village. And what he came up with was this. The head loss, not pressure loss, head loss, is a friction factor. In this case, we're using the Moody friction factor. So it's F subscript M. If you say F subscript F, that's the fanning friction factor. They're identical apart from a factor of 4. So I've got my friction factor. Multiply that by L over D, length of the pipe, divided by the hydraulic diameter. And then I've got V squared over 2G. Hang on, isn't that familiar? Isn't that velocity head? Yeah, it is. It's velocity head. We don't have to worry about that. It's just one of those nice things to remember. So this is nice. But how do I figure out this? Because length of the pipe, no problem. Diameter of the pipe, no problem. Velocity of the liquid flowing through the pipe, no problem. I can work that out really easy. This is the difficult thing. This is where I'm going to spend a little bit of time. Now, what we could do is we could use Colebrook-White's. And we've got this formula here. So what I can do is I can make a guess at the number for F, plug it into this calculation, and see if that side equals that side. It's iterative. You have to do it a few times. Usually 3 is plenty. But there are other ways of doing this. But a couple of things I want to show you now. Look what's in here. Right here is the Reynolds number. I need Reynolds number. And what I've also got is something else here not everyone's familiar with. This is the relative roughness on the inside of the pipe. And relative roughness is that epsilon, that is the absolute roughness. Now for carbon steel, that's going to be around about 45 microns or 0.018 inches, approximately. We divide that by the inside diameter of the pipe, and what we get is something called the relative roughness. And if you look at the different size of pipes here, you'll see that the relative roughness decreases as the pipe size increases. And of course that makes sense because the absolute roughness stays the same because it's carbon steel, but you divide it by a diameter, so bigger diameters have less relative roughness. All sorts of make sense. Okay. Now then, because I think the vast majority of people who are watching this webinar right now are probably engineers. If you're not engineers, you're doing something similar. Maybe you're doing operations, but whatever. You want to know, is there a quick way of figuring out this F factor instead of using that iterative process? And the fact is, there are many. There's a lot of them. And what I've done here is I've just pulled up a bunch. We got Swami Jain from 76. Moody was the original that we used. What we're looking at now is something called the Moody diagram, or a variation of that. There's Haaland in 1983, Fang in 2011, Bellows 2018, and Burkick 2011. And this is only a small example. There's a lot more out there. And what I did was I calculated and put it into an Excel spreadsheet, each one of these formulas, and I looked to see, was there much of a difference? And if you look at this lot, they're all pretty much the same. There's very little difference between them, apart from this one. Bellows, Nalbatis, Sakiris. What these guys did is they developed friction factors, but it's not for pipes, guys. What this is for is flood flow on a plane. The only thing I'm saying is when you're looking at using one of these calculations, just be careful it's for pipe work, because there are other things out there which are not for pipe work, and it doesn't quite work as well. Any of these others, I'm happy. I'm going to use Burkick, and even Burkick has 3 different iterations, 3 different methods of working with it. I'm just going to use this basic one. And this is the Moody diagram using Burkick's calculation. Now, if you look at the bottom here, you'll see that the calculation is actually in 2 parts, and quite a few of them are in 2 parts. And if you look at the basic calculation here, you'll see that the friction factor minus 2 of the log 2.18 beta divided by the Reynolds number times the relative roughness divided by 3.71 to the power of minus 2. All right, horrendous. Put it into Excel, guys. It's easy. You can do this, no problem. But what about this thing called beta? Well, beta is here. And beta is simply a function of the Reynolds number. And of course, you remember the Reynolds number? Our Reynolds number equals rho v d over mu. So that is density, velocity, diameter, and viscosity. Now, all of you guys have calculated a Reynolds number at some time or other. This should not be scary. You plug this into your Excel spreadsheet, calculate beta, plug beta. Oh. Someone, I think I've actually broke my my PowerPoint. There we are, we got it back. Okay. Okay, right, we got it back. Okay, so what we're doing is we've got beta, we're plugging that into here. And what we do is, because we're doing this with different velocities, we get different Reynolds numbers, which is the bottom axis. And what we get is the Moody friction factor. But notice each of these curves are for a different relative roughness. So let's just do a quick example here. We're going to find the Moody friction factor for a flow that's got a Reynolds number of 34,000. So there we are, this is 34,000. It's a 6-inch pipe. The relative roughness is 0.0003, which is right in there somewhere. So we follow this along here, and where it comes up is right there. That's our intersection, and we just read off right across here, and that's our Moody friction factor. In this case, 0.023. Okay, let's do this the hard way now. Let's use our Excel spreadsheet, and we're going to do a calculation. But it's something first I want to warn you about. I think a lot of us have heard about this thing called the affinity laws. And one of the affinity laws says that the friction head loss is proportional to the square of the flow. Now, if you look at the formula, that starts to make a little bit of sense. Remember Darcy? He said F times L over D times V squared over 2G. So really, it looks as if the friction head loss is proportional to the square of the velocity. No, it isn't. Because remember that the Darcy is not an exact equation, as that Fm changes with the Reynolds number. We just saw that on the Moody chart. What I did was I just did a quick calculation for a 10-inch pipe, 1,000 meters long, flowing WTI crude. And when I did a curve fit, what I found was that the friction head loss was proportional to the velocity to the power of 1.82. Scary stuff, eh? This is only applicable for this particular flow in this particular pipe. So you need to check what yours is if you want to do this accurately. But all I'm trying to get away from, guys, is don't think that your friction head loss is always going to be proportional to the square of the flow. It isn't. Okay, quick example. We've got a 0.72 SG, 0.8 centipoise going through a 12-inch line. It's in Schedule 80. It's an A106 grade B, and the flow is 1,200 cubic meters per hour. What's the Moody friction factor, and what will be the pressure drop through 850 meters of pipe? Right, first of all, we're going to calculate the Reynolds number, rho VD over mu. Well, the first thing to do that is I need V. Now, I know I've got 1,200 meters cubed per hour. Well, I know what my pipe ID is because I've got to calculate the cross-sectional area. That comes out at 0.066 square meters. The velocity now is 1,200 cubic meters per hour. Divide by 3,600 to get into seconds, times 0.066, just over 5 meters per second. Do exactly the same with FPS if you want to. The Reynolds number, rho VD over mu, rho is 720. I've got my velocity, and And that's my diameter. That's my inside diameter in meters. And, oh, good grief. Sorry, guys. I don't know what's happening there. My PowerPoint just crashed. Let me start it again. Just stay with me. Maybe I'll stop using that, that adapter. Okay, where are we? I'm thinking about it. Okay. Okay. So the Reynolds number comes out at just over 1 million, 1.3 million. I'm going to use Birkick. So using Birkick, I'm going to calculate beta. And the only thing I really need there is the Reynolds number. And that Reynolds number there is coming out here. It's 11.05. We calculate the Moody friction factor. And that comes out, just plugging in numbers here, 0.014. Now I know what the Moody friction factor is. I can now calculate my friction loss. I'm going to use Darcy. And L over D, 850 over 0.289. V squared, we said was 5.09. Comes out at 54 meters. Convert that into pressure using rho GH. And that comes out at 385 kilopascals. So it's easy. It's not difficult. There's a bit of number crunching going on here. But you know, come on, you guys are engineers. You can do this in Excel with no problem. But we've ignored the fittings because we've only been working with a section of straight pipe. And every different fitting is going to have a different amount of friction losses. Now, there's a quick example here. Let's see if this is working again. Yes, it's working. What we've got is an approximation here of the L over D factor for different fittings. That L represents the equivalent length of straight pipe to give you the same amount of friction loss as this particular fitting. So if you know what the internal diameter is, the hydraulic diameter, and you know the size, and you know what sort of fitting it is, you can easily calculate the equivalent length. Now, we could go a little bit deeper. Don't get too scared on this, guys. All I've done here is I've taken those L over D values for those different fittings, and I've applied it to different nominal size pipe. And here I'm looking at a 6-inch line. If I'm looking at a gate valve, what I see is the gate valve, one gate valve, 6-inch will give me 1.23 meters equivalence. What that means is a 6-inch gate valve will give me the same amount of friction loss as 1.23 meters of straight pipe. So if I know what all my fittings are and I calculate the equivalent length, all I then have to do is add up all those equivalents to the actual length and then go through the same Darcy formula. Now, we're going to do one with a 4-inch pipe. So a 4-inch pipe and a 4-inch gate valve is going to give me 0.82 meters. Let's do a quick one. We've got an atmospheric storage tank. It's got oil with an SG 0.85. And what I see is the line to the pump. Well, I've got 1 meter here, a gate valve, 5 meters, and I've got a 10-meter run, then 8 meters to a branching T, then 4-meter run, then a 6-meter to another gate valve, and then another 1 meter into the pump. So if I want to figure out what the pressure is right here, or the pressure drop from the tank to the pump suction, All I now need to know is what's going on here. So I know it's a 4-inch Schedule 40 A106. The valves are all open gate. The bends are long radius. I've been given the friction factor, and I know the flow. All I do, first of all, is add up all the actual lengths. So 1 plus 5 plus 10, so on, gives me 35 meters. I know I've got 2 gate valves. I've got one here, and I've got one right there. 2 times 0.82, 1.64. Same for a branch T, the same for 3 long radius elbows. And these are all of those equivalent lengths. The total adds up to 47.7 meters. Plug that into Darcy. I get 17.9 meters. And then I convert that using my AARRGGHH. And what I get is 14.96 kilopascals pressure drop from that tank to that pump suction. Stu, I see your cat's still wandering in and out there.
He wants to join.
Oh, let him in, let him in. Okay, so what we've done, we've calculated the friction head loss. We've calculated all the friction loss associated with those additional fittings. And now what we want to do is figure out what the actual operating point is. So that's easy. So I'm going to use my head against flow curve to develop my system. And first of all, I put a straight line on the bottom, which is the static head. And the static head is what we call the elevation head and the pressure head. So this is the elevation head on the suction, looking at the elevation head on the discharge and looking at the difference. That's a total elevation head. I look at the pressure head on the discharge, the pressure head on the suction, look at the difference. That's the total pressure head. It does not change as the flow changes. So that's a straight line. Next, I'm going to add my friction loss. Now, we calculated the friction loss at a particular flow rate. But we said at 0 flow, there's obviously 0 friction loss. So I now have 2 points on my curve. I've got 1 point there where the friction loss is 0. And somewhere up here is where my friction loss was at the particular flow. And remember, we know the relationship between the two of these. And for my particular system, we calculated it's the head is proportional to the flow to the power of 1.82. Or what I could do is I could calculate this for different flows. So that's not too difficult to do. So what we end up with is a system curve. I overlay now my pump curve onto that system curve. And the thing to remember is your pump will operate where the pump curve and the system curves cross. That's always true. So that's your operating point. Easy. So we've got, this is our design flow. This is now my design total dynamic head. And a lot of the time, that's all we do. So we go to the pump vendor who say, yeah, I'll have that pump, please, because that's what I want. That works. But what if? What if those tank levels don't stay the same? What if those tank levels change? What if the pressure in the suction tank or the pressure in the discharge tank start to change? What if, and heaven forbid, what if your control valve starts to operate and you get different friction losses? Good grief, what are you going to do? What you should do is think about those changes. Think about the changes in the static head, but also think about the changes in the friction head. What you end up with is a system operating envelope. This is the information you need to send to the vendors. This is what I would call doing a sensitivity analysis. So you could be operating in that flow, or that flow, and either of those two heads, or anywhere in between, depending on the operation at that particular time. Implications of this. Well, here's one. Let's put our system curve on there. We're going to be working on this pump. We're going to be using the large impeller. So that is my operating point, which is pretty close to best efficiency point, BEP. That's nice. But when I do my sensitivity analysis, there's my system operating envelope. That's my new operating point. I'm right at the end of the curve. The chances are, if I'm operating way down here at the end of the pump curve, my pump is going to be cavitating. You're going to have cavitation problems. Notice that the flows are now substantially different. If we go up to the NPSH curve, what we find at BEP flow, we've got about 2 meters of head, NPSH, which isn't too bad. But if we go to the high flow, our NPSH now, which is now NPSH required, this has now gone up to 4 meters. This now starts to get a little bit scary. You've also got a change in power requirement. There's all sorts of stuff going on. So one thing I want to remind you guys about is you've got 2 ranges in your pumps when you get your data sheets. You've got your preferred operating range and you've got your allowable operating range. Make sure when you do your sensitivity analysis that your pump is not operating outside of those ranges. And the way I've drawn this sensitivity analysis here, that thing over there, I'm outside the allowable range. Over there, I'm outside the allowable range. I would much rather stay within the preferred operating range. But if you operate out there, you are going to get a lot of failures. Now, we do have some backup for this. API 610 or ISO 13709 gives us this information. Head against flow, same as we've got here. That's the pump curve. Number 1 is the allowable range. Number 2 is the preferred range. And this curve here, that's your vibration amplitude. At BEP, the vibration coming from the operation is minimal. But as soon as you start operating at other flow rates, you very quickly find the vibration increases, both high flow and low flow. This is well known, it's well documented. Please make sure that you check this when you get your new pump. It's a good idea to make this part of your commissioning process, just to check what your vibration levels are at different flows. And once you do that, you can correlate that to the allowable vibration levels, and you can check what your allowable region is at the very least. I'm not going to go through too much of this. I'm going to skip quite a few of these now because I've got some information here about cavitation. And I'm sure everybody here knows about cavitation. Every liquid will vaporize, it will flash at a particular combination of pressure and temperature. If you go from this side of the vapor line to that side, you're flashing from a liquid to a vapor. Going back again, those bubbles of vapor collapse, and that is cavitation. And that can be extremely damaging. This is a photograph I was given by a very nice gentleman called Larry Crum. Last time I talked to him, he was a professor in Alaska. And this is an ultrasonic image of a cavitation bubble. And you can see the jet inside as the bubble's collapsing. And these can cause huge pressures, and it will end up causing fatigue erosion on the surface of the material, either on the pump or even on the impeller itself, or even in other parts. And just one quick reminder just before we finish. I said that thing about NPSH NPSH required, according to API 610, ISO 13709, is now called NPSH 3. And the reason for that is the definition of what is cavitation. And what the vendors do is they put their test pump in a test stand. The flow comes in here through the pump, back out through a control valve, through a heat exchanger, back into the tower. We control the pressure in here by either pressurizing or running a vacuum. We maintain the temperature in here nominally about 60 degrees Fahrenheit. And this will be fresh water. And what we do is we check the pump curve. Then what we do is we start to shut in the suction valve, or we reduce the pressure over here until we start to get the onset of cavitation, bubbles start to form, and we lose efficiency. And the pump curve shifts down to here. And once we've got a 3% drop in head, that is classed as the onset of cavitation. And that defines your NPSH for the vendor. So keep that in mind. And just remember that value of NPSH, you're already cavitating. Right, just to finish. NPSH. That NPSHR is a characteristic of the pump provided by the pump vendor. Your test data is obtained by reducing the suction pressure so the head decreases with 3%. It is tested with water. The NPSHA is what you have to determine. That's your mechanical and your process system design. NPSHA for NPSH3 allow a minimum 3 feet or 1 meter margin. Hydrocarbon correction factor. The Hydraulic Institute does allow the use of a hydrocarbon correction factor, but API 610, ISO 13709 do not. You're not allowed to use it. So I'm sorry, guys, this has been quite a rush. I tried to finish in 45 minutes, but it might be 55. The learning points here. What do we actually do? Well, you've developed a system curve, but remember, you need to consider your minimum and maximum liquid levels, your minimum and maximum pressure. Calculate the friction losses for the full operating range. For your NPSH, consider the worst case of suction on the pump. Think of the suction side. That's where you're going to get cavitation. And don't forget about temperature. Because remember, this thing about NPSH is not just pressure. It's that pressure-temperature combination. And then once you've got this, you've got your system curve, you know your NPSH, carry out your sensitivity analysis, and compare that to your preferred and allowable operating ranges. Now, guys, if you do this, your boss will be very happy because you're not going to be getting all those nasty pump failures. You're not going to be getting those seal failures. Your bearings will last for longer. And everyone is going to be so happy. So that's about it, guys. We've been on quite a tour today. And now I'm going to do the little bit of marketing. And I don't care. It's a free webinar. So please come to our training courses when you want to. This information that we did here is all included in ME44. We do have a virtual ME44 in November. And you're welcome to sign up. It is running. It's definitely running. We already have people signed up. There is an online, a Petro Academy version of this, which you can take. It's not quite as advanced as this, but it's good. And in the future, if you still want to go with the free stuff, and that's okay, you can. Next week, we've got Malcolm Harrison, who was a BG Chief Process Engineer. He's going to be talking about the economic drivers behind plant design and operation optimization. That's going to be really neat. I am really looking forward to that one. The week after that, Kendra Snow McGregor, who's actually on this call, I think, is going to be talking about fractionation, optimizing operating conditions to increase efficiency. The week after that, We've got hydrates and hydrate inhibition by Mahmoud Moshfeghin. Mahmoud is an awesome guy. He is so clever. The week after that, we're going subsurface. We got well integrity by Santiago Mojica. And the week after that, Kevin Kyler, who's our Director of Technical Division Operations, he's a specialist in drilling fluids. So he's going to talk about solids in your drilling fluids. So if any of you guys are subsurface, you really don't want to miss either of those. If you're surface, you really don't want to miss those two. Either of you, nobody should be missing this one. Show me the money. Malcolm's a very, very good speaker. A lot better than me. And so, we've come to the end of the session. We still have a bunch of people. I saw that the Q&A window was going crazy while I was talking. Stu, what have we got?
I've been pretty busy here. Where to start? There's a good question here about parallel pumps.
Yeah.
I'm wondering if you could walk us through what happens when you run, let's say you have an existing pump and you add a second pump. If you could run us through what happens to the pump curve and the system curve in that process.
Yeah, sure. All right, I'll tell you, let me just go to a white screen here. Just going to get rid of this. I'm going to put a blank in there, and we can draw on this. Okay. So we're talking about two pumps in parallel, yeah?
Yeah, let's assume it's pumps in parallel versus pumps in series. So we've got an existing pump, and we're adding a new pump to the side of it. And because we've got some new load that's going on, there's a new addition to the plant or some additional flow. And so we've got one pump that was installed in 1960, and then in the year 2020, we added a second pump on the side. And some of the challenges that occur with that process. So I'll leave that with you. I think you know where I'm going here.
I do. Okay, so we got head and flow. So let's think about our system curve first. Actually, no, let's think about the pump curve. If this is the pump curve for one pump, and the system curve, what sort of process was this? Was this a high friction?
Assume that it's a medium friction system curve.
Okay, so let's say our static head starts about here, and then we add the friction to this, and we end up there somewhere. That's our operating point.
That looks good.
All right. We now want to look at two pumps operating. So when you're operating two identical pumps in parallel, what I do is I add the flow. So for this particular head, neither pump will deliver anything. Once I get down to this head, I need to add exactly the same amount of flow, which is going to be there somewhere. When I get down to here, I'm going to be about there. So we draw the curve now, which looks something like this. So that's two pumps operating. The flow with one pump operating is there. So that's your flow with one pump operating. But your new pump curve for two pumps intersects your system curve there. That's your flow with one and two pumps operating together. So you might think by putting two pumps in parallel, you're going to get double the flow. You're not. And it really depends on the system head. So you think about your system curve, think about how much friction you've got in there. There is a way you could get double the flow. Imagine that your friction head was virtually zero. Something like maybe a boiler feed pump. So if I got a boiler feed pump, that's feeding water into a boiler. The elevation head, well, maybe 5 meters. The let's think now. The pressure head is going to depend on what the pressure is in here. But if let's say that was 50 bar, that's going to be about 500 meters. So your static head is going to be 55 meters. How much friction losses do you think you're going to get in there? It's not going to be a lot. Maybe a couple of meters. You add that particular design flow to there, what you've got is virtually a straight line. Oh, I've gone down a bit. So if you had a system curve, if you had a system curve which is static dominant, what you end up with, what you end up with is a straight line here, and you would get approximately double the flow. But the more friction you have, the less likely you'll have to get double the flow.
And the only comment that I'd have to the question, I'm just trying to look for the question in the Q&A blocks, is this dialogue that you can see that Ron's going through here is based around two identical pumps. And when you're adding a new pump to the system, and we're talking centrifugal pumps here as well, you've got to look at adding the two independent pump curves. And so what you'll notice in the discussion that Ron's had here is that by running two pumps, you have affected the performance on the existing pump as well as the performance on the new pump. And so you need to go through this process of, okay, take the two pump curves, add them together in terms of performance, plot them in Excel, put them on top of the system curve, and then work back to each individual pump. And then work out, is one pump going to back out the other pump? How close to the best efficiency points are we going to be operating each pump?
Yep.
And what's the effect on the NPSH of each pump and the power requirements of each pump? So I always go through those series of questions with that process. So hopefully we've answered some of your question there.
Yeah. It's just about bring your points in. I got involved with a system in North Africa on a long pipeline, and they already had some big pumps in. They want to put some bigger pumps in. So if this was the curve of the really big pump, that was the new one, and this was the curve of the pump that was already in existence. When they run the two of them together, the little pump didn't add anything until you got down to about here. And the system curve, well, your new pump took all of the flow and it was deadheading the old pumps. And the old pumps were just tripping out in high vibration. There was a lot of money spent on that project. And I only came into the end. I was actually doing something different. And that was an ODM moment when they realized what the problem was, and they ended up scrapping the small pumps. And that was a lot of money wasted.
Another good question for you here, Ron. Why does the brake horsepower curve not start at zero? Why does it not go to zero? Because when you think about power on a pump, power is equal to flow times pressure divided by efficiency of the pump. Why does pump power not go to zero?
Well, it sounds perfect when you talk about that thing, but it only really works when your pump starts to operate properly. When the pump, let's say your pump has got the discharge valve fully closed. As the discharge valve's fully closed, you've got no flow going through the pump, but you still need some power to keep this thing running. So you've got a couple of things going on there. First of all, you've got a lot of turbulence inside that pump. And don't forget, you've got all the mechanical issues. You're heating up the liquid. You're operating at very low efficiencies. So the calculation that we showed is good for most of the curve, but it tends not to work when you get to very low flows. So it sounds like a doctorate thesis coming up for someone to actually develop that. But that's the simple answer. The simple answer is too much going on.
I've put some of my own answers and comments in here. So based on time and everything, I'm just trying to run through as many of these questions as I can.
Yeah, sure.
There's a fantastic question here that in terms of pump selection, for me, it scratches the wall on so many issues. As a design engineer, what kind of a margin should I consider when I'm designing a new pump. And I'm not sure if you want to run with that, or you want me to run with it. You may want to add a sketch to that or something, and leave that with you.
You know, the temptation is, I've seen it so many times. You start off by saying, in fact, I've got to clear all this off now, haven't I? I'll just go to my annotation and bring it on again. Yeah, come on, come on. The temptation is that if you come up with a design for the pump and you say, yeah, that's good, our pump is it's fine, but what about the future? You know, maybe what we're going to do is we're going to open up some new wells, or we've got some reason that we're going to need more flow in the future. Let's increase the spec of the pump by 10%. So if we look at the pump curve, there's your pump curve there, and let's say that's your best efficiency point. That's where I really would like to operate. So that's my best efficiency flow. So when we do our calcs, that would be our operating point. Perfect. Lovely. Let's add 10%, shall we? Because 10%, we need 10% for the future. So we go and we're now operating there. Great. But in reality, our pump's oversized. So we're actually operating down here somewhere on this pump curve, because we've got a bigger size pump. So we take that in, say, yeah, okay, we've got 10%. And then you go into your boss, and your boss says, hey, yeah, that's a good idea. Yeah, that's great. Hey, we need to add 10% more, which means you're now operating, you've got a bigger pump now, and you're operating even further down the range. And of course, everyone goes, even by the time you get to purchasing, you could end up being way down here somewhere. And if your allowable range is like this, and this is your normal operating point, your sensitivity analysis could be over here somewhere. Which means that a lot of the time you're going to be operating way outside. You're going to be getting low flow cavitation. You're going to be getting bearing failures. You're going to be a lot of seal failures. If you do need to future-proof your pump, buy a pump where the casing will handle all those sizes if it's a single stage. And then you can go in, you can start off by buying a small size impeller. And as the time, everything changes, you can swap that out for a bigger impeller. If it's a multi-stage pump, talk to your vendor, show them what you're doing now, show them what you think you're going to be doing in the future. And what they might do is give you a rotor with a few impellers missing. And so that will put you right in the region for today, but also it will give you that flexibility for the future. So, Steve, what else have you got to say?
Yeah, that's great, Ron. Thanks, mate. My early comment is this: the moment I see design margin and hydraulics, I always kind of freak out, because it's exactly that dialogue. Each time you add design margin, you change the pump curve, you increase the pump curve, and now you're not operating where you'd like to be operating, which is at your best efficiency point, because that gives you best reliability. So really, we aim for a design flow, and that design margin, there shouldn't be one. The design margin should be as small as possible. If you start adding design flows, Ron, you just said it, you went into change the impeller selection. And I would say that's a really good point. When we select a pump, don't go to the largest impeller. Back off one size if you can put a smaller impeller, or allow for spares for future proofing. Make sure that you think about the motor and the drive and the wiring and everything like that, because you want to future proof all of that for the largest impeller, highest SG, worst case scenarios, right? Because the last thing you want to do is, hey, we put in a bigger impeller, but now I need a new MCC section to be able to drive this new pump, right? So,
yep.
Great question. Comes up frequently, and I have to say I've seen lots of pump projects go sideways from that.
Yep. Me too.
So here's another fantastic question. How do we adjust the original vendor pump curve to account for age? My short answer to that, because I've had a few minutes to think about it, and I'll let you percolate, Ron, is testing. So depending on the application of the pump, depending what the pump is doing, you could have a lot of erosion and corrosion to the impeller. And the moment that you start to deteriorate the shape of the blades, the diameter, the tip shape, then you're going to deteriorate the performance of the pump. And so one pump may deteriorate very quickly, another pump may not. So if you're trying from an operations perspective to understand what's happening, whenever we try and buy a pump, we should be asking for a pump performance test curve, and therefore we could take the performance, a couple of pressure gauges or pressure transmitters that are accurate, we could revalidate the performance of that pump back onto that pump curve and evaluate how much erosion or wear has gone on.
Yeah, so, I would say as well, Stu, the reliability guys should be doing this anyway. Your reliability guys should be actually looking at the pump curve and looking at all of the parameters and saying, am I on the pump curve still? Because if I'm still on the pump curve, I don't need to strip the pump.
Yeah, and I think the more complex part of this question is from a design perspective.
Yeah.
So if I think about this and I go, okay, well, it's one thing to have the pump and have the reliability guys engaged, but if I'm a design engineer and I'm trying to specify a pump, and I want it to, how do I account for that as the pump ages? I'm like, now I've got a question that's a bit like, how much corrosion and erosion am I going to get? And so I step now into a material selection and an erosion mechanism type equation and process rather, right? So what things are acting on that pump to deteriorate the pump? And that's where you've now got a question that's very difficult to answer. So typically what I would do there is I would start talking to pump vendors, I'd start talking to other operators in the area, people that are running this pump already, discovering what they're finding in terms of this application and what's working well for them, and then use that data to be able to help me with my material selection for the new pump that you're specifying. I'm not sure if that helps, but that is from a design perspective, that's a very difficult question to answer. And I don't know if I've answered your question there.
I think what I would also do is get into a narrative with a vendor and say, look, this is what I'll accept. If your pump is doing this with this process fluid, how bad is it going to get? And they should have that information.
So there's another question. I'm going to jump question, and I think that we're rapidly sort of running to the end of time here, but
yeah, we are.
That happens. So another question here, NPSH available, and I'm not sure if you just want to focus on that or that and pump head and pump performance. We do all calculations considering density SG based on the pumping fluids. However, NPSH calculation is based on water. How does that vary the performance of the pump when the density is changing? When you have an NPSH curve based on water and you're pumping crude oil, does that affect your NPSH curve? R curve?
I don't think it affects the NPSH curve directly.
So the short answer there is no, it doesn't. We test with water because it's very easy to test with. And as you change the SG, the NPSH curve, you can think of that head as energy going into the front of the pump. It's the suction head. And the NPSH is the difference between the vapor pressure and the suction energy. And so if you change the SG of the fluid, the NPSH will be the same.
Yeah, the only thing I was going to mention was I can't. The only thing that's going to change the performance parameters is really going to be the viscosity.
Absolutely. Thanks for putting that in there. Viscosity correction is a big deal, especially when you get into some heavier, more viscous crudes in colder climates. That has a huge effect on the performance of the pump is viscosity.
Yeah.
And so you'll need to probably talk to your pump vendor about viscosity correction to the pump.
Cool. Anything else that we need to run through?
Yeah, there was another question in here. Sorry, I'm getting hit up from a few different sides. There's a follow-up question on the NPSHA. There is a difference in opinion when it comes to suction velocity. Some experts say that as long as you keep the NPSHA greater than NPSHR, you don't need to worry about suction velocity. And this is a very interesting, it starts a whole lot of very interesting dialogue here about these terms. And the first thing that I would say is, as long as we all realize that NPSHR, if you're operating where NPSHR is approaching NPSHA, you're operating with the pump cavitating.
Yep.
And Ron, you mentioned hydrocarbon correction factor before, and if I'm operating with a propane or an ethane material, they're very, very forgiving when it comes to cavitation. But if you're operating with cold water, you're going to have a lot of issues at that point.
Yep.
And so be really careful about the safety margin that exists between A and R. And so that's kind of my first go-to, right? And then the second part, you start talking about suction velocity. And so there is a term referred to that we haven't talked about in this webinar here. We talk about suction-specific speed. And suction-specific speed starts to get into the suction energy requirements at the inlet eye of the pump. And this starts to tie back to this suction velocity idea. And so there are some very interesting papers as your suction-specific speed, and I'm thinking in foot-pound-seconds units, approaches 10, 11,000, we talk about suction stability and needing to try and either reduce RPM or increase the net positive suction head available to them on that calculation. And so that might be some guideline that helps with that. There's also some rules of thumb out there where a lot of pump vendors say, hey, keep your suction velocity under 3 feet per second. And I've seen a lot of pipeline applications where the suction pressure is well above the NPSH requirements of the pump, but the suction velocity is higher than that 3 feet per second. I've seen that fairly commonly out there.
Yeah, you could consider that this suction velocity is just a knob that you dial to get the right NPSHA. Yeah, and I guess if I'm working in an application where I'm very sensitive about cavitation, I would bring my velocity down. And if I'm in a midpoint pipeline booster station where I have a lot of margin from my vaporization point, then I can probably tolerate smaller piping and a higher velocity. Yep. I'm not sure if it goes much more than that or if we've answered your question well, but it's a great question there, Hitesh. Okay, I think we're starting to lose people now.
So how about this, guys? Great discussion. If there are questions that we didn't get to during this, what we'll do, folks, is when we send out the recording, we'll include a transcript of the Q&A, and we will follow up on any questions that we didn't get to during the actual discussion. That way we're respectful of everyone's time here. So, hey, Stu, Ron, thank you guys very much. Ron, thanks for the great presentation, and then Stu for facilitating the discussion. That's good stuff, guys.
No worries. Thanks.
Thank you.
Thanks, guys.
All right.
Thanks for your time, guys.
For joining us.
And don't forget,
have,
we have more training courses coming up, so sign up, look at the website.
Absolutely. Thanks, everybody. Stay safe, and we'll hopefully talk to you soon.
Thank you. Bye.
Bye all.
All right. Thanks, guys.